So today we're starting section 3.1 over the idea of functions. So functions are probably something that you're familiar with from your other math classes, but in this math class, since we're at a little bit more advanced level, we're going to look in a little bit more detail at functions than you might be used to in your other math classes. It's also possible that you've already seen a lot of this. For example, if you took college algebra with me, as I know a few of you have in the past, you might know a lot of these ideas already. Okay, and I've also divided this section into a couple parts. The first part, we're going to talk about kind of the basic idea of a function. And then in the next part, we're going to talk about some of the functions that are important in computer science and discrete math. So the kinds of things that you would use when you're programming, let's say, or writing an algorithm. So let's just dive in. A function, the way that they're commonly thought about, and this is the way that it's even taught in math courses sometimes, is as a rule that assigns one member of a set X to exactly one member of a set Y. So this language is a little abstract. Let me make it more concrete. In most math classes, we write functions like this. F of X is equal to some rule. We could do a simple one like 2x plus 5. Okay. So this is a rule that tells you what to do with the number X to get a new number. So if X was the number 1, let me just write that out. If X was the number 1, then we would just plug in 1 here to get 2 times 1. Yes, this is being recorded. I did start the recording a second ago to answer that question in the chat. 2 times 1 plus 5 would be equal to 7. So this is a rule that assigns the number 7 to the number 1. Point to the right spot. Okay, so we're going to make this definition a little bit more rigorous on the next page. But before we get there, I want to do this example of what's called a checksum. So it's an interesting little application of a function that you might use in computer science, like if you were setting up a website to accept payments, credit card payments. So a checksum is one method that's used to detect errors in credit card numbers. So it's not, strictly speaking, a security measure. Its purpose really is to check to see if the number was copied down correctly. Oops. Get my words in the right order. Credit card numbers. So when you're copying down a number, especially a long number, like a credit card number, some things can commonly occur, like maybe you just type a digit wrong, or maybe you type 2 digits in the wrong order. And a checksum is a way to see if that has happened. So if you actually copied it down correctly, or if there was maybe a mistake. And what we're going to do is work through how a checksum works. This is a hypothetical credit card number. It's not an actual credit card number, or at least I hope it's not anyone's actual number. And we're going to work to see how a checksum works. So what a computer would do to see if the credit card number was entered correctly. And The first thing that we should discuss is the last number here. I've boxed it. This last digit is what's known as the check digit. So this is how we're going to check that the credit card number was actually written down correctly. And then we're going to use the rest of the numbers to do an operation to check against this number. And what we're going to do first is double every other number starting at the right, so starting at 5. Let's see, do we have enough room here? Yes. So double every other number from right to left. Starting after the check digit. So we'll double the first one to get 10. The next one we copy down, double the next one to get 8. And then we just continue this. So the next one gets copied down. 7 gets doubled to 14. 3 is copied down. 1 is doubled to 2. 2 is copied down. 8 is doubled to 16. 5 is copied down. 3 is doubled to 6. We bring 0 down. Double 9 to 18. 6 is copied down. And then finally, we double 4 to get 8. Are there any questions so far in what we're doing? There are still a few steps left to do, just making sure everything is clear so far. Okay, and then the next step, since it doesn't seem like there are any questions, is to add any double-digit numbers that we might have created. So add the 2 digits. And all the other numbers will be left alone. So for example, 10 will add 1 and 0 to get 1. And then 6, 8, 5 all get copied down. 14 will add 1 and 4 to get 5. And then we'll copy down 3, 2, 2. Here's another 2-digit number. We add 1 and 6 to get 7. Bring down 5, 6, and 0. 18 will have to add 1 and 8 to get 9. And then finally, we just bring down 6 and 8. Okay, we have a couple more steps to do to check our credit card number. The next step is just to add up everything, to take the sum. So that'll be 8 plus 6 plus 9 plus 0 plus 6 plus 5 plus 7 plus 2 plus another 2 plus 3, and then we have 2 5s to add, and then finally 8 and 6 and 1. Okay, so quickly do the sum in your head. Or not, I can just tell you the answer. In practice, a computer. Oh, well, someone already did it. Maybe you have the textbook open. Or maybe you're just really fast at addition. If you already did it in your head, then you're faster than I am. Calculator, yeah. Yeah, in practice, this is something that a computer program would be doing. So it would happen almost instantaneously. Just long enough for the processor to do the math. Okay, so we have our sum. We've taken our credit card number, this long number, and we've distilled it down to a much smaller number. And there's one more step. If the last digit of the sum is 0, then the number 0 is our check digit. So otherwise, like in this case, we need to subtract the last digit from 10 to find the check digit. So our last digit is 3. So we're going to come down here and just do 10 minus 3 to get 7. And this is what is called our check digit. So what we would do now is compare this number that came out of our algorithm, our function, compare 7 to the check digit from the credit card number, the one that we boxed at the beginning. And you can see that they're the same. So the check digit on the credit card is 7, and when you do this mathematical operation, we can confirm that the card number was copied down correctly. Or this is at least one check for that. Are there any questions over the process? Okay, so it doesn't seem like there are any questions. So the idea behind this algorithm, this checksum algorithm, is that it catches very common errors. And I mentioned the most common earlier. So for example, if we wrote, instead of a 3, if we wrote a 4 here, then in our checksum, we would have doubled 4 to 8. And instead of having a 6 down in our sum, the 6 here, it would have been the number 8. So it would have increased our sum to 75, which would have led further down in the process to a different check digit. So this algorithm can check to see if a single digit was copied down incorrectly. And your textbook works through an example or several examples where this happens if you want to go take a look. And it'll also detect if two numbers were entered in the opposite order. So if we had a 5-3 instead of a 3-5 here, then instead of 3 getting doubled, the number 5 would have been doubled to 10. And then we would have added 1 and 0, and then we would have had a 1 down here in our sum instead of 6. And there would have been another change here in this calculation. 3 would have been passed down to here. So it'll detect this transposition problem. So like I said, it's not strictly speaking a security measure, it doesn't check to see if the person who has the number is really the authorized user. It just checks to see if they entered the number correctly. So if you want to try this on your own credit card, your textbook makes a note of a few different credit cards that use this algorithm, this particular algorithm. Let's see, should have remembered. Yes, there we go. So if you have a Visa card, a MasterCard, or a few others, American Express, or Diners Club, not familiar with that one. But these four credit card companies at least use this particular method of checksum to check to see if a credit card number was entered correctly. So this algorithm that we worked through is actually used in the real world all the time. So anytime you enter your number on Amazon or any other website where you're ordering something, the computer system is going to perform this operation to see if you entered your number correctly. Okay, so still no questions? Okay, so we've looked at the kind of intuitive idea of what a function is based off of what you kind of, the impression that you get from your math classes, I think. This is the intuitive definition of a function. And this idea of a function, it could be something like this checksum. So this method, even though it was fairly complicated and doesn't really feel like the same kind of rule, it was still a method that started with an input. So this here. So all but the last digit of the credit card number was our input. And then we had some method, which was fairly complicated in this case, that output a number. So 7 was our output. Let's see, put this in here. So functions can actually be in practice much more complicated than the kinds of simple functions like lines and parabolas and cubic functions that you've seen in your algebra courses. So what we're going to end with today is a discussion of the more rigorous definition of what a function is using set theory. And then we're going to look at a few simple examples and just think them through about whether they really are functions or not. Okay, so here is the real rigorous definition of a function. So we need two sets. Let x and y be sets. Then a function from x to y, go ahead and write that word in, is a subset of the Cartesian product x cross y. Okay, so we'll need to talk about what that means in a second. There's a little bit more, though, to the definition. So it's a subset of x cross y, where for each x in the set x, so each element x in your set, there is exactly one element y in the set y with the ordered pair x, y in the function f. So this definition can feel a little weird because I'm talking about a function as a subset of a Cartesian product. So a function, maybe just put this as a note off to the side, a function is a particular kind of set of ordered pairs. So right away, this rigorous definition is very different from the intuitive one, where a function was a rule that assigned an input to an output. Okay, and there's a little bit of notation that comes along with functions. The shorthand mathematical notation looks like this. So you write a letter for your function, and then a colon, and then here you have the set x with an arrow pointing to the set y. And the translation, if you wanted to convert this back to English, would be something like this. F is a function from the set x to y. So when you see these symbols written down in a homework problem or your textbook, or maybe you need to write these symbols on your homework, this is what it means in English. There's a few more parts of the definition that we need to give names. The sets x and y are given specific names. You probably already know these. So x is called the domain. These are the things that we think of being plugged into the function. And the output is y. That's the codomain. Okay, good question, William. The codomain is a little bit different from the range, and I'm about to write down what the range means in this set theory notation. The range is a subset of the codomain, but it's only the particular values that show up here in the function f. So it's the outputs that are possible from our function. And in set builder notation, we would say the range is the set of y such that an ordered pair x comma y is in the function. So it's only the possible outputs. I should have given myself a little bit more room here because there's one more thing I need to say. So this ordered pair notation is closely related to the other kind of notation where we think of plugging in a number x into a function and having an output. Because if we have some ordered pair in our function, so if x comma y is an element of the function f, then we write, or we can write, f of x is equal to y. So this is how the ordered pairs are related back to the old idea. So we think of x as the input and y as the output. Are there any other questions over the definition before we look at an example and try to decipher what the definition means? Okay, so it seems like there aren't any questions. So let's move on to our first example here. Maybe I'll put a little horizontal line in here to separate things a little bit. There we go. So in this example, X is going to be the set containing 1, 2, and 3. Y is the set containing the 3 letters A, B, and C. And my, I don't want to call it a function yet, but my set F is this set of ordered pairs, 1B, 2C, and 3B. So I don't want to call it a function quite yet, because I'm going to ask the question, is this set actually a function? This is what we want to answer. So what I'm asking you to do is to check whether it satisfies the property up here in the definition. So it's a set of ordered pairs, but does it have this extra property where for each X in the set X, there is exactly one Y in the set Y with an ordered pair X comma Y in the set F. That's what we have to check and sort of decipher along the way. And what we're going to do in these small examples is something called an arrow diagram. And this illustrates how F pairs elements of the sets X and Y. And they're relatively simple, even though we give them this kind of special name. What we're going to do is make 2 columns. The first column is going to be for X. So we write down the numbers 1, 2, and 3. And we might want to draw an oval around these elements just to show that they're all in a set together. And then we want to make another column for Y. This will have the letters A, B, and C. And just do the same thing. So an oval or just a blob to show that they're all in a set together. And then for each ordered pair, we're going to draw an arrow from the first element to the right element. So for the first ordered pair, I'm going to draw an arrow from 1 to B. Then I'll draw an arrow from 2 to C. And then finally, I'll draw an arrow from 3 to B. like so. And if f is going to be a function, what this translates to, this set theory definition, what it translates to is there needs to be a single arrow for each element in this column for x. So let me just write that down. So if f is a function, there will be a single arrow from each element of x to an element of y. And each arrow tells you how the input of your function x from x is paired with your output of the function from y. 2 y values. So you're close. If a line intersects 2 y values, so like this one, we have 2 different lines, 2 different arrows pointing to b. This is fine, actually, as long as we have a single arrow from each element over here. So the problems happen when you have 2 arrows from a single element over here in the x column. Yeah, and you might have seen this in your algebra class, that's right. So does each element from x have a single arrow to an element in y? In this function? Or this, excuse me, you don't want to call it a function yet, for this set. Well, we can just look. There's a single arrow from 1 to b, a single arrow from 2 to c, and then a single arrow from 3 to b. So this is actually a function. In this example. Okay, so this is one method to determine if a function or if a set of ordered pairs actually is a function. Before we move on to another example, though, I want to discuss what the domain, codomain, and range are of this particular function, since we have checked. I guess we should start with the domain, not the codomain. So what is the domain of this function? Anyone? What values are being plugged in? Well, it's this set here. 1, 2, and 3. What's the codomain? So these are the values in the set y. We don't actually have to do any work, just like we didn't have to do any work for the domain. We were told y is equal to ABC, the set A, B, and C. But we do have to do a little bit of thinking about range. So remember, range is only the possible y values that come out, the possible outputs of our function. And it could be that there are some values of the set y that are missed by our function, so there's not an arrow pointing to them. Someone tell me the range of this function, and I'll just wait a minute until someone answers. Okay, thanks, William. Yeah, it is B and C. And in the arrow diagram, it's fairly simple to see the range. So it's the set that you have arrows pointing to. So in this case, we have arrows pointing to B and C. Good. Okay, any more questions before we look at a couple more examples of these ordered pairs? Okay. And I left off one label in my arrow diagram. So often you'll label the arrows with the name of your function. So in this case, we'll label them F. Now let's move on to the next example. So we're given new range in codomain and a new set of ordered pairs. And we want to do the same kind of thing and determine if F is a function. And when you have these small sets like these, where you only have a few elements, I would definitely recommend trying to draw an arrow diagram. It's possible to answer without them, but this just really illustrates the idea of what a function or something that's not a function looks like. So you'll want to make two columns as before, one for X and one for Y. In this case, our set X is a little bit bigger because we have 4 elements, 1, 2, 3, and 4. Label that X, and then make another column with the 3 elements A, B, and C. Maybe label that one Y. And then for each pair in the set F, we're going to draw an arrow from the first element to the second element. So we'll start with an arrow from 1 to A. Then an arrow from 2 to B. And then an arrow from 3 to C. Okay, so looking at the arrow diagram, can anyone tell me if F is a function? Good, Samuel. It's not a function. And we can see the reason from the arrow diagram. We should find an arrow from each element over here, a single arrow to another element of Y. So we have one for the number 1, we have one for the number 2, we have an arrow for the number 3. But when you come down to 4, there's no arrow pointing to the set Y. So that's a reason there is no arrow from 4. And going back to the set theory way of thinking about things, there's no ordered pair with 4 as its first element. Right, William. So you can't plug 4 into F. That's right. There's no defined output. So before we move on, we should always think about three things. Oh, well, never mind. Those are three things that we want to think about for functions. We'll leave them off here. We can think about those later on in a different section. Are there any questions? Any other questions about the second example of something that's not a function? Okay, so since there aren't any questions, let's go ahead and move on to our last example today. So here we're going back to the original two sets. X is going to be 1, 2, and 3, and Y is going to be the set with A, B, and C. And now we want to consider this new set of ordered pairs from X cross Y and answer the same question: is F a function? Okay, so by now you have some practice. We know we need to make an arrow diagram. So we'll start with a column for X with 1, 2, and 3. And we'll make another column for Y. Maybe I'll fill in the letters first. A, B, and C. And then we go to the set F, and then we draw our arrows for each ordered pair. So here we'll have an arrow from 1 to A. Then we'll have an arrow from 2 to B. Arrow from 3 to C. And then finally an arrow from 2 to A. So is F a function? Would someone like to answer? Good, Caden. F is not a function again in this example. So the reason here is that there are two arrows pointing from 2 to elements in the set Y, whereas we should have just a single arrow from each element over here. Two arrows. From 2. And going back up to the ordered pairs, we can see that there are two ordered pairs where 2 is the first element. So there are two, and I should specify different pairs. In F with 2 as the first element. So there's an important distinction that you need to remember. It's perfectly fine if there are two arrows pointing to a single element over here. So it's perfectly fine that there are two elements pointing to A, for example. The real problem, the thing that makes this not a function, is that there are two arrows from 2 pointing to the right. Okay. So that is our stopping point for today. Does anyone have any questions here at the end of class?